Imagine standing on Venus, a world where the air itself is trying to kill you. The ground beneath your feet glows a dull, suffocating orange. The sky above you is orange. The rocks, the horizon, the light, everything is bathed in the same hellish amber haze. The temperature is 475 degrees Celsius, hot enough to melt lead. The pressure on your chest is equivalent to being crushed under 1 kilometer of ocean water. And the clouds above you, the thick, unbroken blanket that hides this nightmare from the rest of the solar system, those clouds are made of sulfuric acid. This is Venus, and it is not the peaceful twin of Earth that scientists once believed it to be. For decades, Venus was sold to us as a gentle world, a sister planet wrapped in soft white clouds, sitting comfortably inside the sun's habitable zone. Some astronomers in the mid-20th century imagined a warm, wet, tropical paradise hidden underneath that cloud cover. They pictured swamps, humidity, maybe even life. The Soviet Union believed this so deeply that their early Venus probes carried instruments specifically designed to detect water. They expected to find a second Earth. What they found instead was a planet that destroys everything it touches. So what makes Venus the deadliest planet in our solar system? The answer is not one thing. It is everything, working together in ways that feel almost deliberately hostile. Let's start with the atmosphere, because the atmosphere is the first thing that will kill you. Venus is wrapped in a blanket of carbon dioxide so thick and so heavy that the surface pressure reaches 90 times that of Earth. To put that into perspective, you would need to dive roughly 900 meters below the surface of our ocean to feel the same crushing force. No unprotected human body could survive for even a fraction of a second. Your lungs wouldn't just fail, they would be physically compressed flat. The atmosphere doesn't just press down on you, it presses in from every direction, like being sealed inside a vice that never stops tightening. And that carbon dioxide is not just heavy, it is a trap. Sunlight enters the atmosphere and reaches the surface, but the heat that radiates back up cannot escape. The carbon dioxide catches it, holds it, and sends it back down again. This is the runaway greenhouse effect, and on Venus, it has spiraled completely out of control. The result is a surface temperature of roughly 475 degrees Celsius. That is hotter than Mercury, even though Mercury sits tens of millions of kilometers closer to the Sun. Mercury has almost no atmosphere. Venus has too much. It is not proximity to the Sun that makes a planet deadly. It is what the atmosphere does with the energy it receives. That temperature is constant. There is almost no difference between the day side and the night side, between the equator and the poles. On Earth, nighttime brings relief. On Venus, there is none. The heat is everywhere, all the time, radiating from the ground like the inside of a kiln that has been running for billions of years. If you placed a bar of lead on the surface, it would slowly soften and melt. Tin and zinc would not even stand a chance. Now rise above the surface, up into the clouds. You might expect some relief up there. You would be wrong. The clouds of Venus are not made of water vapor. They are composed primarily of sulfuric acid droplets. Concentrated sulfuric acid, the same corrosive chemical found in car batteries, but far more concentrated. These clouds form a thick, unbroken layer that wraps the entire planet, reflecting roughly 75% of the sunlight that hits them. From space, Venus looks like a bright, featureless pearl. Underneath that pearl is an acid bath suspended over a furnace. These sulfuric acid clouds do produce rain, but here is the disturbing part. The rain never reaches the ground. The drops of acid fall from the cloud layer, descend through the increasingly hot atmosphere, and evaporate long before they touch the surface. This phenomenon is called virga. It is acid rain that boils away in mid-air, cycling endlessly back up into the clouds to condense and fall again. A toxic loop with no end.
And then there is the wind. At the surface, the winds on Venus move at roughly 0.5 meter per second. On Earth, that would barely rustle a piece of paper. But on Venus, the air is 60 times denser than our atmosphere. A breeze that slow still pushes with real physical force. Higher up, things change dramatically. At the cloud tops, winds scream around the planet at over 300 kilometers per hour. The entire upper atmosphere circles Venus in just 4 Earth days, even though the planet itself takes 243 Earth days to complete a single rotation. The atmosphere moves 60 times faster than the planet beneath it. Scientists call this super-rotation, and despite decades of study, no one fully understands what drives it. That rotation itself is another piece of the puzzle. Venus spins backwards. Nearly every planet in our solar system rotates counterclockwise when viewed from above the North Pole. Venus rotates clockwise. If you could stand on the surface and see through the clouds, the sun would rise in the west and set in the east. But you would be waiting a very long time. A single day on Venus lasts about 117 Earth days. And here is where it gets truly strange. A day on Venus is longer than a year on Venus. The planet takes 225 Earth days to orbit the Sun, but 243 Earth days to spin once on its axis. Time itself is twisted on this world. This backward, crawling spin contributes to another deadly feature. Venus has no significant magnetic field. Earth's magnetic field is generated by the churning motion of its liquid iron core, driven in part by our planet's relatively fast rotation. Venus spins too slowly to generate the same effect. Without a magnetic field, there is no shield against the solar wind. Over billions of years, that relentless stream of charged particles stripped Venus of whatever water it once had, ripping hydrogen atoms from the upper atmosphere and scattering them into space. The evidence of this loss is written in the chemistry. The ratio of deuterium to hydrogen in Venus's atmosphere is roughly 100 to 150 times higher than on Earth. Deuterium is heavier and harder for the solar wind to carry away. The light hydrogen escaped, the heavy hydrogen stayed behind. It is the fingerprint of an ocean that was slowly torn apart, molecule by molecule. This is one of the most haunting aspects of Venus. Billions of years ago, the planet may have had liquid water on its surface, conditions not entirely unlike early Earth. But as the sun gradually brightened, and as volcanic activity pumped more carbon dioxide into the atmosphere, the temperature rose. The oceans began to evaporate. Water vapor is itself a greenhouse gas, so the evaporation accelerated the heating. The heating accelerated the evaporation, a feedback loop with no off switch. Eventually, all the water was gone, baked into the atmosphere, and then stripped away by the solar wind. What was left was a planet locked in a permanent state of thermal runaway, a world that cooked itself to death. And it is still cooking. For decades, scientists debated whether Venus was geologically dead. That debate is now effectively over. In 2023, Robert Herrick at the University of Alaska Fairbanks went back through archival radar images taken by NASA's Magellan spacecraft in the early 1990s. He compared images of a volcanic vent near Mart Mons taken 8 months apart. In the first image, from February 1991, the vent was roughly circular and covered less than 2.5 square kilometers. In the second image, from October 1991, the same vent had doubled in size and appeared to be filled nearly to the rim with a lava lake. It was the first direct evidence of volcanic activity on Venus. Then, in 2024, an Italian research team led by Davide Sulcanese found evidence of new lava flows in 2 additional regions. The researchers concluded that volcanic activity on Venus could be comparable to that on Earth. There are over 80,000 volcanic structures on the Venusian surface. The planet has more volcanoes than any other world in our solar system, and at least some of them are still active. This matters because volcanism feeds the deadly atmosphere. Volcanic eruptions release carbon dioxide and sulfur dioxide directly into the air. On Earth, rain washes sulfur dioxide out quickly. On Venus, there is no rain that reaches the ground. The sulfur dioxide accumulates, rises, and becomes sulfuric acid. The volcanoes are chemical factories feeding the toxic sky.
We know all of this because of machines that gave their lives to tell us. The Soviet Venera program ran from the 1960s through the mid-1980s, and it remains one of the most extraordinary engineering efforts in the history of space exploration. The early probes were built based on faulty data. In 1967, Venera 4 was designed to withstand 20 atmospheres of pressure. It entered the atmosphere and was physically crushed at an altitude of 27 kilometers. The next 2 probes tried to fall faster by using smaller parachutes. Both imploded 11 kilometers above the surface. For Venera 7, the engineers abandoned the concept of an aerospace vehicle entirely. They built a submarine, a forged titanium sphere capable of withstanding 180 atmospheres. The parachute failed during descent. The probe crashed, toppled onto its side, and its signal was buried in static. It was only during a post-mission review that scientists found 23 minutes of temperature readings hidden in the noise. The first transmission from the ground of Venus. Later missions pushed further. The engineers turned each lander into a temporary heat sink. Before separation, they pumped supercooled fluid through the pressure vessel, bringing the internal temperature down to -10 degrees Celsius. The probe essentially began its mission as a block of ice falling into a furnace. Inside, they packed lithium nitrate trihydrate, a chemical that absorbs enormous energy as it melts. This gave the lander roughly 50 to 60 minutes before the heat won. In 1975, Venera 9 reached the surface. Scientists had expected total darkness. They were wrong. The light levels were comparable to a cloudy summer day. The images showed sharp, angular rocks, not the smooth pebbles they had predicted. In 1982, Venera 13 survived for a record 127 minutes and captured the first color images. Everything was orange. The rocks, the sky, the horizon. The atmosphere absorbs blue and green wavelengths, allowing only red and orange light to reach the ground. A human standing on Venus would see the world in permanent sepia tone. The lander's calibration chart confirmed it. The white strip appeared orange. The blue strip appeared nearly black. Venera 13 also captured the first sounds ever recorded on another planet. A low, constant drone as the thick atmosphere flowed over the lander. Then the crack of the drill firing and the grinding of the bit cutting into basaltic rock. And then there was Venera 14, which landed 4 days later. One of its instruments was a spring-loaded arm designed to strike the ground and measure its hardness. Upon landing, one of the protective lens caps popped off and landed directly on the spot where the arm was about to strike. The arm hammered the titanium cap instead of the Venusian soil. The engineers had navigated millions of kilometers, survived re-entry, and landed in hell, only to be defeated by their own safety equipment. After 1982, no camera has looked at the surface of Venus from the ground. We have sent rovers to Mars that stream high-definition video. We have flown past Pluto. Yet for the planet closest to Earth, our visual understanding of its surface is frozen in images from over 40 years ago. NASA's Veritas and Da Vinci missions, along with the European Space Agency's Envision, aim to finally change that.
Venus is Earth's twin in size, in mass, in composition. It sits in the habitable zone of our star. It may have once had oceans and a climate not so different from our own, and yet it became this. A planet where the air can crush a machine, where acid falls from the sky and evaporates before it touches the rocks, where volcanoes still feed a toxic atmosphere running on a feedback loop for billions of years. Venus is not just a dead world, it is a warning. It is proof that a planet with all the right ingredients can still go catastrophically wrong. And the most unsettling part is that the same greenhouse physics that turned Venus into a furnace operate on Earth too. The difference between our world and that one is a matter of degree, not of kind. We look at Venus and we see what Earth could have been, or, if we are not careful, what it could still become. Thanks for watching, and I'll see you in the next one.